Hello there, WINDPOWER students. I'm glad to welcome you to our lecture that's going to be about wakes. This is a chapter in your textbook. It's chapter 7. We are not going to cover everything that's in chapter 7. A lot of the stuff that's in chapter 7 kind of explicitly relates to work being done at the employer of the author of your textbook, and it's a little bit wonky and a little specialized to what they do. It doesn't fit very well into the broader context of wind power. And so, because this isn't a whole graduate course in wake turbine dynamics or something like that, we thought we would just probably hit some of the basics of how a wake works and some of the basic wake models and so on. I like what your book did right at the beginning of chapter 7, where the author showed this famous picture of wakes from a wind farm off the coast of Denmark. I believe the name of this wind farm is Horns Rev, which I don't have any idea what Horns Rev means. But clearly, something is happening here that we need to understand. I mean, as I look at this image, it's awfully hard to make sense of what's going on, both in terms of the dynamics as to what's going on with the wind, and what's going on as to why is there something visible here. Okay, it's obviously something like cloud or fog or something like that, but we'll get to that. Your book, by the way, actually does give you the reference to an article in Popular Science or Nature or something like that, where they actually very thoroughly dissect what's going on in this picture. You might find that interesting and clever to read that and find out what's all going on and why is it visible and why and so on. But that's not where we're going with this. But let's just kind of zoom in and figure out what's going on here. So if I just sort of zoom in to take a closer look at this picture here, I can see, well, clearly the wind is coming from the viewer into the screen, and it's setting up something we're going to call a wake. And whatever this is, it's clearly affecting the turbines that are downwind. Now, it wouldn't have had to be exactly like this, the way it's shown in this picture here. It just so happens that in this particular picture, it was snapped at a time when the wind was blowing from an upwind turbine towards a downwind turbine, but clearly has an effect, and somebody spent a lot of money to build those turbines. They're probably not happy if this is reducing the amount of power these turbines are producing, or maybe they're very happy if it's increasing the amount of power these turbines are producing. We're going to have to sort that out. Whatever the effect is that's going on with these wakes, clearly that effect is getting wider and wider horizontally as you go downwind from the first turbine. You can see how that wake, which is visible for some reason in this picture, again, we'll get there, it's clearly getting wider and wider as we go out. That's clearly going to have to be something we're going to need to be able to explain about turbines and their wakes. And actually, once you zoom back out on the picture a little bit, it becomes clear that whatever this wake is, it's getting deeper as we go downstream from the first upwind turbine. You can kind of see, if you look at this with a little perspective, that cloudy, foggy, whatever it is layer is getting deeper and deeper as we get farther downwind from the original turbine. And if you take a good look at it, it's got a lot of little swirly motions. There's places where this cloudy fogginess is kind of higher and lower. It looks pretty turbulent to me. So clearly whatever this wake is, it's turbulent. Okay, we're going to have to explain that. And it's also visible. I mean, normally when a wind turbine is operating, it's not visible to see the wake. Why is it visible here? Well, it happens that the conditions were just right in this case to make this wake visible. It's an example of a phenomenon that in the atmospheric sciences we call saturation by mixing. And saturation by mixing is a fascinating and important phenomena in lots of meteorological things. And it just so happens that this is perfect conditions in this particular day, at this particular location for a saturation by mixing. Saturation by mixing is when you take, sorry, there's a timer going off. When you take two air parcels that are not saturated, and therefore the humidity is less than 100%, and you combine them and you get saturated conditions and droplets of water start forming and it becomes visible. And the classic example of this is when you can see your breath in the winter. You see your breath in the winter when warm, moist air inside your lungs, but it's not saturated, it's not foggy inside your lungs, but when that air parcel that's inside of your lungs comes out your nose and your mouth and mixes with the air around you in the winter, which is also not saturated, but because the combination of exactly the temperature, pressure, moisture inside your lungs and the temperature, moisture, pressure, density, all that kind of stuff outside of your lungs. It just so happens that when the air mixes, you get the right conditions in the winter that you get saturation. The same is true of like when your car's engine is running at on a cold winter day. When the warm, relatively moist air parcels coming out of the tailpipe of your car mix with the colder, drier air parcels outside of the car, they result in by saturation by mixing the saturated air parcels. This is also how contrails behind a jet engine work and so on. Well, all we're seeing in this diagram here with this situation here with these wakes behind these wind turbine at sea is another example of saturation by mixing. We are mixing air with one temperature and humidity and pressure and so on kind of down around the level of the ocean with air parcels that have a different temperature, pressure, humidity a little bit above that, and it just happens that it is a proper combination of temperatures and pressures and humidities that we get saturation. The actual mechanisms of that are fascinating, but this is not atmospheric physics, this is not atmospheric thermodynamics. We are not going to go into the details of how it works. The point is, we got lucky when this picture got snapped. It just so happened that the right combination of temperatures and pressures and humidities of air parcels were right by each other. The mixing action of the turbulent wakes behind the wind turbines mix them, and we get something like fog or cloud, tiny little drops of water that make this wake visible. That's all it is. Okay, we're not going to bog down in the details of how that all happened. We don't have the background in moist thermodynamics in this class. Okay, if your book wanted to throw a definition of wakes at us, your book would suggest this definition. It would say it's the area behind the wind turbine affected by the fact that the wind turbine takes momentum out of the wind. That's what a wind turbine does, right? Wind turbines extract kinetic energy slash momentum slash whatever. I mean, there's slight different definition, but it reduces that. And, well, back when we were way back in Module 1, when we were learning about the basics of kinetic energy and Betz's law and stuff like that, that's what the turbine does, is it extracts it, but then the flow responds to that. The flow has to deal with the fact that there has been a change in the momentum of the air, the change in the flow has to spread out downwind from the turbine and so on. We'll reflect back on that in just a little bit. So what your Chapter 7 in your textbook does is it breaks this idea of wakes down into three kind of applications where we need to worry about wakes. Chapter 7.1, I believe it is turbine-to-turbine wakes, which turns out to be practically the entire contents of the chapter. And then two shorter topics, wind farms, where the wakes are interacting with each other, and inter-farm wind farm wakes, where you're worried about like how one wind farm affects another wind farm, which might be quite a few kilometers away or something like that. Again, those topics 2 and 3 kind of are a whole lot shorter. We really want to spend our time on the basics of turbine-to-turbine wakes. Okay, so if we're going to focus on this idea of turbine-to-turbine wakes, in some ways this term, turbine-to-turbine wakes, is a little bit distracting. The name refers to the fact that we're talking about the impact of an upwind turbine on a downwind turbine. It's a turbine-to-turbine wake. Now, it wouldn't have had to be a turbine that was downwind. We could be talking about like a weather station or an anemometer or something that was downwind of the first turbine. It's called a turbine-to-turbine wake because that tends to be the application that wind power professionals are interested in, right? They want to know how the wind is being affected at the location of a downwind turbine by the one that's upwind. That affects things like how much power is being produced and how turbulent the flow is at the location of the second turbine, which affects turbulent load and the lifetime of the moving parts of the turbine and so on. So the name turbine-to-turbine kind of just refers to the fact that that is what wind power professionals are thinking about, but in practice it could have been a turbine and a weather station, or a turbine and some other, that's not the issue. The downstream thing is just sort of effectively just measuring the wind. So, let's kind of picture this setup I have right here. And we're going to say that the wind is blowing along a line that goes from an upwind turbine directly to a downwind turbine. And the one that is downwind is of course being affected by the fact that the upwind turbine is taking some of the kinetic energy of the wind and converting it into mechanical energy of the rotor and the drive shaft and the high-speed, low-speed shaft and the gearbox and ultimately driving the generator. That is extracting kinetic energy out of the flow and the flow is adapting to it. Now, I kind of like this figure that your textbook uses to kind of illustrate the three-dimensional geometry of these wakes. So we have two panels. I don't remember what the number of this figure is in your book, but the top panel here is the top view. We're looking down on the rotor, and you can kind of see the nacelle is that grayish, darker gray line there. And we're looking down on a turbine. The wind is going from left to right, and you can see that gray area there is the wake of the turbine. That is sort of starting off with the same width as the rotors themselves, the diameter of the rotors, and then widening out as it goes downwind. The bottom panel is showing you the side view of the same thing. Again, now you can see the tower and the nacelle and the rotor in that direction easier. And you can see that the wake doesn't just widen, it also gets thicker. Thicker in the sense of a greater distance between the bottom and the top of the wake as you go downwind from the rotor. So the rotor starts out with the same, the wake starts out with the same thickness as the diameter of the rotor, and then as we go downwind, the the wake gets thicker and thicker. We have a three-dimensional, think of it as sort of like a cone spreading out, kind of a cone with a point cut off of it, spreading out from the radius of, from the diameter of the rotor, spreading out downwind. Now, the fact that it's spreading out is in some ways not terribly surprising. We actually saw that back in the context of Betz's law. This is literally a slide I just captured back from Module 1, the lecture about Betz's law. And we had that plane, we were building a diagram here where flow was going through a certain cross-sectional area of the blades, A1, and as it passed through there, it started to expand out to a new cross-sectional area, A2, as it passed through there. It was necessary, you can even see the text on that slide there, that the flow has to be slower and it has to spread out as it passes through the plane of the rotor itself and going downwind. That was part of how we were able to determine things like the efficiency of the rotor and the turbine. So we did that way back in Module 1. Now, how does this actually happen and what can we know about the speed of the winds and so on? Now, right behind the blades themselves, the flow is incredibly complex. You can go online to like YouTube or Google image search or something like that and see animations and 3D visualizations of what the flow is like in that first few tens to few hundreds of meters behind the rotor itself. But you'll see that it's ridiculously complex. As the blade is tearing through the air at, well, the tip of the blade, remember, might be going more than 100 miles per hour. The flow is incredibly complex. It's kind of carved into these sort of spiral-shaped vortices. The flow is basically, it's not possible to really define like a speed to the flow. Okay, the flow is extraordinarily turbulent in those first few distances downstream. Let's be more clear about this. For a forward-facing hot, we tend to describe the distances downstream in terms of a unit called D, the rotor diameter. So like that blue area, that's the first maybe 2 to 4 rotor diameters, or 2D to 4D downwind from the turbine itself. We don't even try to explain what the wind speeds are doing. In many ways, the wind speed isn't even really a defined thing. You wouldn't stick an anemometer there, it wouldn't be giving a meaningful representation of what the winds are doing and so on. The flow is just too turbulent. But for that matter, you wouldn't put a second turbine that close to that first one anyway, so who cares, right? I mean, this is not a practical thing to be worried about. Okay, then you have farther downwind, more than maybe 3 or 4D downwind from the original rotor. You have this big, long wake. And from as little as our understanding of Betz's law to a complicated understanding of wake dynamics, whatever level at which we would understand it, I think it makes good common sense that we will expect the speed of the wind to be weaker downstream. Because regardless of what else has happened in the craziness of all the turbulent flow right around the rotor itself, we know that the net effect has been to extract kinetic energy from the air. And doing that has resulted in the flow being weaker as you go downwind. Now, we should be able to use this common sense sort of understanding about what's going on in the wake just crude level of like, well, it should be slower and it should be turbulent. I mean, that makes pretty good sense. We should be able to use that to get us a better understanding of some of the more complicated ideas, like why is the wake getting thicker and thicker, thicker again meaning that distance from the top to the bottom, as we go downstream from the rotor itself. And I'm going to give you the punchline right away so we can see what we're building toward here. The answer as to why the wake is getting thicker and thicker and thicker as you go downwind is turbulent mixing with environmental air. Environmental air being the flow that is in the area around the turbine but did not actually pass through the turbine. We're going to call that environmental air. And we're going to be mixing air that did go through the turbine with air that did not pass through the turbine. Let me show you what that's actually going to mean. Let's actually pick some distance downwind from the turbine, and I'll call that distance x. We are x meters downwind from the turbine, and I've made like a little slice through the wake right there, highlighted in blue. At that distance from the turbine itself, inside of the wake, the wind has some speed. And we're going to call that wind speed U sub W, or UW. That will be the speed of the wind inside the wake. The subscript W means in the wake. For that matter, though, there is also the air that did not pass through the turbines itself, and we're going to call, or at least has not been affected by the turbines. Let's put it that way. Hasn't been affected by the turbine yet. And we're going to call that wind speed UI. Why is it an I? I never found a good explanation as to why it's I. My guess is that that's from like initial or something like that. Like it's the initial wind speed, but I don't know. It's UI. Alright. Let's actually zoom in as to what the boundary between the top of the wake and the air that is outside of the wake, but above the wake. So I kind of use my magnifying glass in here to zoom in on that part of this little diagram right here. The gray part that's kind of the bottom half of the magnifying glass is inside the wake. And then there's a boundary between the top of the wake and air that has not been affected by the turbine. You can see the wind speed is UW, down inside of the wake. And there's wind speed outside the wake is UI, that initial or environmental or whatever you want to say wind speed. And so on the edges of the wake, right there on that edge between the top of the wake and the environmental air around it, there is a gradient of wind speed. Remember that nice word, gradient? Meaning like there's a change with respect to distance. As we go like a meter up, there is a change in wind speed. There's a change, partial U, partial Z, or whatever, a change in wind with respect to height. Now, that's existing in an environment that's full of turbulence. I drew turbulence as all these little swirling motions inside of, that we're seeing with this magnifying glass. We saw them. We could actually visualize them with that cool picture from Hornsrev. But it should be turbulent, right? We know that the flow inside of the wake is turbulent as heck because of all the motion of the turbine itself, and frankly, even outside of the wake, we're in the boundary layer. It's going to be more turbulent than not. I mean, it should be, having a whole bunch of turbulence is not a big surprise here. So, we need to think about what it means to have turbulence when there is a gradient. Well, we actually talked about that in the turbulence module, didn't we? Anytime you have turbulence, another way to think of it is mixing. Anytime you have mixing in the presence of a gradient, what happens is things start to spread out. They tend to smear out and become more even, right? If you had turbulent mixing of some conserved property with the mixing that becomes more uniform. We did the example of like talking about cakes, right? You put the cake mix in, and there was mix over here, there's eggs over here, and whatever, chocolate or something over here in the bowl, and when you have mixing, it all becomes more uniform. In a room, if I open a bottle of perfume over here in the room, there's a high density of the perfume molecules near the perfume bottle, but if I have mixing in the room, with time, all of the room has a roughly uniform amount of perfume molecules. And in the same way then, across this slice where we have a gradient, in this case a gradient of velocity, then the velocity is going to become more uniform due to all this mixing. Which means that like at a little location, maybe a few centimeters to meters above our wake, where currently the air is not affected by the turbine, the wind speed at that location right now is UI, the initial or unaffected wind speed. But by turbulent mixing with air that is slower, it's going to come up with some new velocity that is somewhere between UW and UI. But by definition, that means that its velocity has been affected by the turbulence and the wake and so on. Therefore, that location that I have right there, that little red dot, will become part of the wake too. See what's happening here? By definition, if our wake means you've been affected, your velocity has been affected by the turbine, well, every step of the way as you go downwind, a slightly higher area has been affected by the turbine, just because the lower momentum winds inside the wake have been mixed a little higher into the environmental air around the turbine. It can only get deeper with respect to distance from the turbine itself. As that lower momentum air just gets mixed a little higher and a little higher and a little higher, by definition, you're increasing the height of the turbulence. So the wake can only expand vertically as you go downwind. And this actually has another consequence, though, for the structure of the wake. See, all this mixing of slower momentum air inside the wake with higher momentum air outside the wake, is a two-way street. Higher momentum air from outside the wake is being mixed into the wake, which means that inside of the wake, air parcels with higher momentum that didn't go through the turbine are getting in there, increasing the average wind speed inside the wake. So as you go downwind from the from the turbine itself, your wind speed is going to get, your UW, your value of the wind speed inside the wake, is going to increase. So like at this first black air parcel that I have drawn that's not terribly far downwind from the turbine, our value of UW is going to, by necessity, have to be very small. Well, I guess it depends how efficient your turbine is, but it's going to be smaller because some of its kinetic energy has been converted into mechanical energy of the turbine. But farther downwind, UW is going to have to be bigger as environmental air that did not pass through the turbine and has more momentum mixes into the wake and increases the average velocity inside the wake. And in fact, if you go even farther downwind, at some point you'll have mixed in enough momentum from outside of the wake into the wake that your air parcel has a wind speed that is effectively the same. Your wind speed inside of the wake, UW, is effectively the same thing as the wind speed outside of the wake, at least to within, like, the measurement error and things like that. And, well, that's what being outside of the wake means. UW equals UI means that wind speed is no longer being affected by the turbine itself, and therefore we are out of the wake, and that's why our diagram eventually ends. See how the gray wake there? At some point we reached an end to it. Now this is not drawn to scale. Remember that our unit for downwind as to how far we are will be in terms of rotor diameters. And I don't know, I can't really very well eyeball it. But I mean, that blue air parcel there only looks like it's maybe 4 or 5 rotor diameters down from the turbine itself. In the real world, 10 rotor diameters might not be a bad guess. But it's not really to scale here, but that's okay. We'll actually make some adjustments to this diagram later to make it more to scale. But there is a kind of a key insight I do want you to get from this diagram here that is something your book doesn't actually mention and doesn't even use a notation that makes very helpful. And that is this idea that UW, the wind speed inside of the wake, is in fact a function of x, how far downwind you are. I mean, that makes sense. You know that the wind will be most affected by the turbine near the turbine, and the farther and farther you go downwind, the wind speed will be closer and closer back to what it was before. The wind speed will have recovered. So UW really ought to be like UW of x, like with, UW parentheses x. And your book never even once writes it that way, despite the fact that would be both mathematically more correct and maybe easier to think about. So, okay, alright, so we've got this idea of these, what this wake should look like, vertically. Like, why is it getting thicker and thicker with respect to distance? I think we've answered that question. Now, let's explain why it's getting wider with distance. Again, we're going to shift to the other half of that diagram in your textbook, where we have a top view of the wind turbine. And you can see the flow coming in from the left towards the right, and we're creating a wake that's originally the diameter of the turbine itself, but it widens as it goes out with respect to distance. And actually, it's the same exact process. We are going to be having the same process of the turbulence that's inside the wake itself, working with the gradient of velocity between inside of the wake and outside the wake, gradually, as the turbulence transfers the lower momentum wind inside the wake to greater and greater distances away from the center line of the flow, you're going to be making the wake wider and wider. Okay, this is not exactly rocket science once you know how it works vertically. In horizontal way, it works exactly the same. I was tempted to drop the word isotropic, as in the turbulence is isotropic. Strictly speaking, isotropic, remember, means that the magnitude of the turbulence in terms of like standard deviation of the flow in the u direction and the v direction and the w direction are all exactly equal to each other. You have just as much turbulence in the vertical direction as you do in the horizontal direction, and so on. I don't think this quite exactly meets that definition. I mean, it would be lovely if it did. If the turbulence were isotropic, your flow would be your wake would be getting thicker at exactly the same rate. It's also getting wider, and so on. In practice, I don't think that's necessary. But you do have to have turbulence both in the vertical plane and in the horizontal plane to make this work as described. Okay, before we go on to part 2 of our lecture, let's answer a couple quick questions about what we just saw. Question 1. When we describe our problem as being a turbine-to-turbine wake problem, we're concerned about how blank. A, an upstream wind turbine is affecting a downstream wind turbine. B, a downstream wind turbine is affecting an upstream wind turbine. Or C, 2 turbines, one upstream and one downstream, are affecting each other. Which of these is the correct way of articulating what it means to be that we're talking about an turbine-to-turbine wake problem? Alright, make a choice from those 3 options and get a little feedback before you go on to question 2.